So the wavelength will be 10 millimeters. You may also be given the distance between two. Did I make a mistake? Another mistake?
Was that not 3 nodes?
Yeah, so this is a node, that's 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 a node. But the wavelength, right? The wavelength is like, so if I, that's the wavelength, right? So it's from here, from this node, not to that one, that would be half a wavelength. This is lambda over 2, and this is lambda over 2. So the wavelength is this. That's lambda.
But did
No.
you say between 2 nodes?
So if I tell you the distance between two nodes, two adjacent nodes, I think I said adjacent. So if I tell you this distance, if I tell you that that's 5 millimeters, that means that this is also, that's another 2 adjacent nodes, that's another 5 millimeters. So the wavelength is this, right? That's the wavelength. And that would be, well, 5 millimeters plus 5 is 10 millimeters. You're still looking happy.
I'm just confused because I thought you said 2 nodes, so why wouldn't it be lambda over 2?
Right, so yeah, you could also do it like that. So lambda over 2 is 5. So lambda over 2 is 5 millimeters. But I asked, what is the wavelength? What is lambda? Well, 2 times, that'll be 10 millimeters. Yeah, I see what you were thinking of. Yeah, you're right. What I gave you was lambda over 2. But then the question was, what's the wavelength? So now solve for lambda, which is going to be twice 5. Or conceptually, right? I mean, this is a wavelength, right? And I gave you this. If that's 5, this has to be 5, so the wavelength is 10. Right? Just going by the picture. So now I see what you were thinking. That's correct. Good. Okay. Should we move on to the next chapter? On sound.
How many chapter 16 stuff is
Okay, so this is just an example of a mechanical wave. So there are some basic, things you should know. So sound waves can travel in air, in a gas. Sound waves can travel in a liquid. Sound waves can travel in a solid. I can hit a solid, and then wave will travel along the solid, and that's a sound wave. And sound waves travel faster in a solid than they do in a liquid, more slowly in a gas, and sound waves do not travel in vacuum. So sound waves do not travel in vacuum. There's nothing to vibrate in vacuum. Sound wave is, when I speak, the air in front of me is made to shake front, back, and then that one shakes the air that's in front of it, front, back, forward, backwards, and that one shakes the air forward. And eventually, there's air, in your ear over here, and that pushes and pushes, moves forward, backwards, and as a result of that, it pushes your eardrum, and then, you end up hearing. But if there is vacuum in this room, and I were to speak, or attempt to speak, first of all, there wouldn't be anything to vibrate in the room. And if there's no air in this room, there wouldn't be air over here to push against your eardrum, your tympanic membrane. So then you wouldn't hear. So sound doesn't travel in vacuum. But it travels in a gas. Sound travels in a liquid faster than in a gas. And it travels, in general, faster in a solid than in a liquid. It's the opposite of electromagnetic waves. When we move on to another chapter and we talk about electromagnetic wave propagation, light being an example of an electromagnetic wave, light waves, for example, light waves can travel in vacuum. And proof of that is that we can see the sun. Well, during the day, and it is not cloudy, right? Of course. You know, between the sun and the earth, you could say that there's vacuum between the sun and the earth, but we can see the sun. So when we see the sun, that's light that's reaching our eyes that came from the sun. And those light waves were able to travel through vacuum and reach our eyes, right? And so light can travel in vacuum, sound cannot. Light travels more slowly in a gas than in vacuum. And light travels even more slowly in a liquid like water than in air, for example. And light travels even more slowly through glass, which is a solid. So light travels the fastest in vacuum, more slowly in a gas, more slowly in a liquid, even more slowly in a solid. Sound is the opposite. Sound travels the fastest in a solid, and more slowly in a liquid, even more slowly in a gas, and it doesn't even travel in vacuum. I said last week, I think it was, that the speed of a wave depends on the medium that the wave travels through, properties of the medium. I think I have a formula in here somewhere for the speed of sound in air. When it's not windy, just calm there. So sound travels at 331 plus 0.6, multiplied by the temperature of the air in, the C in the subscript over there means that's the temperature expressed in degrees Celsius. And then when you put in the numbers in there, then, for the temperature of the air in degrees Celsius, then you get the speed of sound in meters per second. So that's in meters per second. And G, how fast does sound travel in air if the air is at 0 degrees Celsius? Air, calm there, not windy. So if the air is at 0 degrees Celsius, how fast would sound travel? 331 meters per second. And how far is that in 1 second? Roughly, what's 300, from where to where is 331 meters? How long is a soccer field? Or a football field, for that matter? From goal to goal, roughly. 100 meters. 100 yards, 100 meters. A yard is like a meter, so roughly 100 meters. So 331 meters per second means that sound can travel a distance, roughly 3.5 soccer fields in 1 second. That's fast. But then again, it doesn't compare to light. Sound is fast, right? Imagine, if Leo Messi could run 3.5 soccer fields in 1 second, my goodness, it would be unfair. Totally unfair. But light can travel around planet Earth in the same 1 second that sound can travel the length of 3.5 soccer fields. Light can travel, around planet Earth 7.5 times in 1 second. So there's just no comparison. Light is fast, much faster than sound. And having made that statement that light can travel a distance equivalent to running around the entire planet Earth 7.5 times in 1 second. It's interesting to note that when you look at the sun, let's say at the end of class you step outside and you just happen to, I'm going to check out the sun, for a brief moment. When you look at the sun, that light, those photons that just arrived in your eyes, they actually left the sun 500 seconds in the past. It takes light 500 seconds to travel from the sun to the earth, on average. 500 seconds. If in 1 second it can go 7.5 times around planet Earth, can you imagine the distance in 500 of those seconds? And that means that when you step outside and you look at the sun, you're looking at it as it was 500 seconds ago. Just roughly 8 minutes and 20 seconds in the past. So you're really looking at the sun as it was in the, 8 minutes and 20 seconds in the past. The next star after the sun is Alpha Centauri, and it takes roughly 4.5 years for that light to travel from that star to your eyes. So if you go out tonight and you say, oh, that's Alpha Centauri, you're looking at it as it was when you were in high school. Not me, but you. Or most of you. But it's light that left. The star may not even be there. It might have exploded, if it's one of those stars, and you just are unaware that the thing exploded. This is going to take 4.5 years or so for that light to reach your eyes. Resulting from the explosion. So it's interesting that, there are these, well, anyway, light is fast, and we're going to come back to the discussion of light. Let's go back to sound. Frequencies of sound. Well, humans, humans with healthy ears, right, can hear sounds that range in frequencies from about 20 hertz to about 20,000 hertz. Roughly 20 to 20,000 hertz. I remember that my first year in college, I was 17, and I think I could hear up to like 21,000 hertz. But then after age 20 or so, it's downhill from there. Me at my age, I probably hear up to 15,000 hertz. Most of you can, most likely hear up to 20,000 hertz. Some more, some less, but it's like an average. So the audible range of frequencies of sound is from about 20 hertz to about 20,000 hertz. And by the way, that doesn't mean that sounds